Hello, everyone. My name is Joseph, and today with my colleagues, John, Yassin, Sherif, and Jacqueline, we're going to present to you our thesis project titled Automatic Language Feature Migration. This project is supervised by Dr. Karim Ali, Dr. Nadi, Dr. Sherif Aly, and it's a collaboration with IBM Canada. So let's start by defining what is language feature. So in any programming language, a language feature is a capability or functionality that it provides to the developer. For example, in Java, one feature or language feature is lambda expressions, which was introduced in 2014 as part of Java 8 to provide the programmer with a concise way to write function interfaces using a short block of code which takes in parameters and returns a value. So after we define the language feature, let's define what does the migration term mean. So as time goes through, a programming language might have versions that are upgrading. And in one version, a feature can be upgraded, and in another version, a feature might get deprecated and replaced with another new feature. So from a programmer's perspective, this process of upgrading features is called migration, and it's done for two main reasons, which is modifying performance and mitigating incompatibilities. And to elaborate, in our project, we are concerned with a specific kind of migration in which replacing one feature with another does preserve the overall program logic and behavior. Let's walk you through a simple migration example to get a better sense of what a migration is. So in this example, we have a predefined list of numbers from 1 to 10, and we check, we iterate over this list, each number in this list, and we check whether it's even or odd. And if it's even, we print it out to the user. Pretty simple, 2, 4, 6, 8, and 10. And that is one way to write this logic. After introducing lambda expressions, we can write this same logic in this way. So this is a same predefined list. And now we will use for each on the numbers list, which will take a lambda expression, which will be applied to each element in this list. Now we check whether it's even or odd, and we print it to the screen. So pretty simple. And now these two code snippets have the same logic and same behavior. And this process of replacing one library with another or one functionality with another while preserving the overall code behavior is called migration in our project. So when we deal with big or massive projects with thousands of files and millions of code lines, we have the problem of like doing these migrations manually. It's time consuming, it's error prone, and it's boring. So programmers are looking to automate this process. So the goal of our project is to solve these problems by developing a tool that automates the process of feature migration. So the task of the tool would be given a code written in a specific language that uses a specific old feature in this language. Its task is to migrate it to use a newly introduced feature in this same language. However, tackling this general case would be very complex because we don't want to tackle each language, each programming language, and each feature in each language. So we narrow it down to Java to be our main programming language, and all threading libraries and Loom to be the features we're going to migrate between. But what is the old threading libraries and what is Loom? So a thread basically in Java is a direction or path that is taken during the execution of a program. And threading is necessary for concurrency and parallelism, and it's mainly used, or it's widely used in applications related to databases and server-side applications. Another feature that is introduced in Java to do concurrent execution is completer feature, and it has three main features, which it achieves asynchronous execution. It has a lightweight switching compared to the old Java threading libraries, and it solves a limited number of threads per process problem. Why we are introducing this feature? Because it has been seen that it's widely used through wide code bases, so it's worth understanding how it works because we're gonna migrate it to use Loom. Now let's dig deeper into what Loom is. So before Java 19, there existed a library called Java Threads, which enabled us to create and manage physical threads. And these physical threads had many problems, such as they were heavyweight, they were coupled to the hardware's physical threads, they had a high cost of creation and context switching. So to solve this problem, as part of Java 19, Project Loom introduced virtual threads, which are lightweight, they're not coupled to physical threads, and they have low cost of creation and context switching. And another feature they provided, they are easier to write than the physical threads. So now Yassin will walk us through why this problem is not a trivial problem to tackle.
Okay, so some of you might think this problem is trivial or it's easy to implement, since if in case Java 19 or Project Loom has backward compatibility with all threading or concurrency mechanisms in Java, but that's not always the case. So some cases are simple and some cases are complex. So for example, this first example is a simple example of migration. So first we have an executor service, which is created as a thread pool. A thread pool is a group of threads that are pre-initialized to be run, to have tasks run them right away. And in our case, it has a fixed size, which is 4. So if 4 tasks are running on them and another task is submitted, it will be queued or put on a queue. And in this simple example of ours, we have 4 tasks. First, we start the system, and then we block on it until it finishes. Then we get data from both server B and server A, and block on both until they are finished, and then we combine both and return the result. So in order to migrate this simple example, we'll just create a thread factory that's virtual by adding the of virtual keyword. And this thread factory, which is virtual, will be passed as a parameter to the executor service. And that's just a simple example of how migration might be simple in some cases. But that's not always the case, as some examples might be complex. So recall the computable feature that Joseph just explained a while ago, which allows for asynchronous execution of tasks. So we will be using completable features to implement the same program or sample program. It has the same 4 actions. First, we have supply sync, which will start the first action, which is starting the system. And then compose will block on it until it's finished. And then another supply sync will start getting data from server B, and then combine async will start getting data from server A and block on both until they are finished and merge their data in the action of merge data. After merge data is finished, and then blocks on it, and when it's finished, it prints the result. So let's take these 4 actions, main actions, separate them from the rest of the code in order to perform the migration, put them aside, implement each as a task that's submitted to an executor service. And since we want to migrate to using virtual threads, we'll be creating another virtual thread factory and pass it to this executor service in its creation. And thus, as some of you might notice, we have the same exact migrated code as that of the first example. So some of you might think this is simple or easy to do, but this is trickier than the first example. And now that we have discussed how non-trivial the problem is, Jacqueline will walk us through the prior solutions.
Now we'll look up at the prior solutions and how they actually helped us with finding or with our methodology. So first, we looked at the first technique we found was migration history mining, which uses code bases that have already started to adopt a new language feature in order to find patterns. However, we don't have a lot of code bases that have been migrated to Loom, and therefore it wasn't really applicable in our case. But we did use it in order to find the first. In order to find the first step in our methodology, which is looking at the documentation of Loom and Java threads in order to find patterns manually. The second part of our methodology was finding a client project in order to apply those patterns, and I'll expand on this further in the next slide. Another set of migration techniques was comparing different library versions using either static analysis or text similarity. However, with text similarity, it also depended on having code bases that have been using Loom in order to train the data, so we couldn't use it. With static analysis, it was found to be promising, and however, some of the techniques were limited to one-to-one mappings, and with Loom there are many-to-many mappings and one-to-many mappings, which is actually what will contribute in this project. With finding a target client project, we wanted it first to use threads extensively and thread pools in order to migrate from physical to virtual threads. And the second thing was we wanted it to be complex enough in order to monitor non-trivial performance change, as well as testing our migration tool. So the candidate projects that we've considered were Open Liberty, Tomcat, Undertow, and Wildfly, because threading in general is an important part of Java servers applications. So the first candidate project we've started exploring last semester was Open Liberty. However, due to its limitation with the using preview features, it wasn't able to be seen by the compiler. So we moved on to another use case, which was Tomcat, and we have started using Tomcat during this semester in order to apply the found patterns. So what is Tomcat? Tomcat is a Java application web server and servlet container that actually uses threads and thread pools extensively in its architecture. So we have started using it. And using it this semester, and now actually John will walk us through how we use it throughout the semester.
Okay, now moving on to how we tackled the problem. First of all would be the generalization and pattern finding. What do we mean by a migration pattern? A migration pattern is some snippet of code with some specific characteristics that when found, we have discovered a very neat and quick solution that can actually migrate it without actually working on the entire portion of the code. So now I'll be walking you through the patterns that we found. The very first pattern is a bit trivial. It's a one-to-one change of code. It's for whenever a thread is instantiated using the keyword new thread, using the constructor of the thread object. It's fairly simple to migrate. You just use the off-virtual method for the thread class and create an unstarted object and give it the same runnable. Fairly simple. The second pattern also is very similar. It is triggered whenever we have the off-platform keyword. We change it to use the off-virtual keyword. Then for pattern 3, it's a little bit more tricky because it's used whenever we have an executor service. So an executor service is basically whenever we have a thread pool that contains thread, like in the example that Yassin explained earlier. So how do we migrate thread pools? Whenever we have a thread pool, we create a virtual thread factory, which is an object introduced in Project Loom. And then we pass this factory as a parameter. But then if there is already an existing factory, we migrate the factory and then use it, creating an obstacle in implementation. Pattern 4 is concerned with the completable future, like the example that also Yassin explained. We did mention that completable future represented a big obstacle while tackling this problem. But we discovered that all the asynchronous functions that are used with completable future can get an executor as a parameter and then use that executor. So this we can create a virtual executor and pass it to all asynchronous function calls, making it use the new Project Loom. And last but not least is one of our most complex patterns is whenever we have whenever we have a class that extends completable future, which can be done for a variety of reasons, instead of migrating all the function calls, we can do the migration internally in the class itself. Now, moving on to how these were implemented, we considered a variety of ways, the first of which was the very obvious string manipulation. But string manipulation proved to have a lot of corner cases, making it a not really easy to tackle approach, because we'll have to handle all the corner cases by hand. So we moved to use an abstract syntax tree, which is a tree-like representation of the source code that captures the syntactic structure. So just to get a sense of how abstract syntax tree works, let's go through how the first pattern is implemented. So as you remember, the first pattern is just an instantiation of a new thread object. This is an abstract syntax tree that represents exactly that. The very first step in order to migrate this would be to copy the arguments, then delete the entire object creation statement, leaving us with just a thread called myThread. Then we equate it to a method call expression of thread.offVirtual.unstarted. And last but not least, we reconnect the arguments, ending with the final output code. This was a trivial example, but this is a demo for our project. So we start with a vanilla version of Wildfly, and then we run our project. We just give the code the directory for Wildfly, and then it asks if we want to apply the updates in batch or one by one. We tell it to update everything in batch. Now it's going through every single file, telling us if there are updates or if there are none. It takes a bit of time since the project is huge. And at the end, it tells us that it updated 57 files, and it tells us the differences in some of them. So some of them has no edits, and some have insertions, some have deletions. And last but not least, if we go back to Wildfly, we can see that there are a lot of updates that happen, namely the 57 files, and we can see some of them in context here, creating new variables, adding new parameters all around the code. So moving on. Okay, now for our experiments, we had two kinds of experiments. The first was to test the correctness, how correct is the actual code produced by our tool is. And a secondary sort of experiments was to test the performance of Project Loom and how much improvement happened. So for the correctness, the very first test, the first thing that comes to mind would be if the code produced compiles, then it's a good sign. So that's the very first thing that we checked. Next, that we have the fact that the execution yields the exact same result for stress testing and running the unit tests themselves. Last but not least was comparing the migrated results to ground truth that was migrated by hand. This was not used for everything, but was used for some hand-picked example to make sure that everything is running smoothly. For our correctness results, we migrated 3 different server applications, Tomcat, Wildfly, and Undertow. We have a variety of for the number of migration. The success rate for Tomcat was 912 out of 918 tests, so giving us a 99.34% success rate. For Wildfly, it was 99.005, and for Undertow, it was 85.7%. I want to remind you that these tests are for units, complete units, not just a single test. For the pattern heat map, for the very first pattern was the most used, which is the simplest one. Pattern 3 was the next in line. It was also used multiple times. Pattern 4 was only used in Wildfly, and the second and the fifth pattern were never used in any of the migrations, because as we expected, pattern 5 is very rare to find. The performance setup, for the performance test, we tested everything. We tested Tomcat on a machine that is equipped with an Intel Core i9 10900F processor and 64 gigabytes of RAM. We asked Tomcat to serve us 3 different pages. The very first has 0 seconds delay to represent a very simple page. The second has 100 millisecond delay to represent a simple database call, and the last represents an extensive process that takes 5 complete seconds, and the tests were ran before and after migration for 10 times, and the median was recorded. These are our results. For the no delay case, we received around a 10% performance gain. For the 100 millisecond and 5 millisecond, we did not receive such a significant performance gain, but then our project is more concerned with the correctness rather than the performance. The performance is really up to Loom. Now, Sherif will tell us about the future plans.
Okay, so moving on to the future plans and recommendations for our thesis project. We did have a couple of ideas that we wanted to implement, but we didn't have enough time to implement during the semester. So we gathered up 4 main points as our future plans for our thesis project. First one is implementing automatic rule parsing. And this is for the user to write new rules in an XML file or JSON file. And second point is developing a widely available plugin rather than a command line tool. And this is we thought of this because we wanted to give the programmer a better experience and a more easier way to handle the migrations. Third point is adding a testing module, and this is we thought of adding a testing module to pass the commands to a module to run some tests on the code before and after the edits, yielding some beneficial statistics for our project. Fourth point is extending to other newly introduced Java 19 features like Project Valhalla. Moving on to our conclusion, we can conclude our thesis project in a very brief 2 points. First point is identifying the patterns, and what I mean by identifying the patterns is that after analyzing the patterns of the code, we extracted some migration patterns and we used them to feed our tool. And this helped us for automating the migration process. And this leads us to the second point, which is automating the migration process, just like my colleague John demonstrated in the demo. So that's it. Thank you.